Gravity is the first force you ever felt. Before you understood language, before you had memories, you felt it pulling you toward the ground. And for your entire life, that word has stuck: pulling, attracting, drawing toward. It feels so obviously right that almost nobody questions it. Isaac Newton didn't question it. He just described it brilliantly, and the description worked so well that we used it for 200 years to build bridges, predict tides, and launch rockets. But there is a problem. The pull isn't real. Mass doesn't reach across space and grab anything. What's actually happening is so much stranger, so much deeper, so much more beautiful than a pull that once you understand it, you will never look at a falling apple the same way again. I want to walk you through the real explanation today. Not a watered-down version. Not a metaphor that sort of gets close and then waves its hands. The actual physics. In plain language. Because this is one of those rare ideas in science where the truth is more surprising than any simplification of it, and where understanding it changes not just what you know, but how you see every single thing around you. Let's go back to the beginning, to Newton. In 1687, Isaac Newton published a law that said every object in the universe with mass attracts every other object with mass. The strength of this attraction depends on the masses involved and on how far apart they are. The farther apart they are, the weaker the pull. Double the distance, the force drops to 1/4. The formula is precise, clean, and extraordinarily powerful. With this single law, Newton explained why the moon stays in orbit around Earth, why the planets move around the sun in the specific paths they follow, why objects fall when you drop them, why ocean tides rise and fall in rhythm with the moon, why comets sweep in from the outer solar system and loop back out again. Everything clicked into place. The universe, for the first time, felt like a machine running on understandable rules. And for over 2 centuries, that was enough. Engineers built on it. Astronomers predicted with it. Ships navigated using it. The equations worked everywhere they were tested. But Newton had a private unease that he never fully resolved. He wrote about it honestly, which I admire. He could describe exactly what gravity does. He had no idea what gravity is. He could not explain how the sun, sitting 93 million miles away, managed to reach across all that empty space and tug on the Earth. What was doing the tugging? Through what medium? At what speed? He called it action at a distance, and admitted it was deeply unsatisfying. A force that operated across empty space instantaneously with no visible mechanism. It worked in the equations. It didn't make sense as a physical picture. Newton left the question open, and it stayed open for 228 years. Then Einstein answered it, and his answer was so different, so unexpected, so structurally alien to how anyone had been thinking about gravity, that even today most people haven't fully absorbed what he said. Einstein said, there is no pull, there is no force at all. What we call gravity is the geometry of space-time responding to mass. Let me build that idea up from scratch, because it has several layers and each one matters. First, what is space-time? Before Einstein, space and time were thought of as completely separate things. Space was the 3-dimensional stage on which events happened. Time was the independent clock that ticked in the background, the same everywhere, for everyone. They were unrelated. Einstein's special theory of relativity, published in 1905, showed that this separation was wrong. Space and time are not independent. They are woven together into a single 4-dimensional fabric called space-time. How much space you measure between 2 events and how much time you measure between them depends on how fast you're moving. 2 observers moving at different speeds will measure different values for both space and time, but they'll always agree on a combined quantity called the space-time interval. Space and time trade off against each other, but together they form something consistent and unified. This was already revolutionary, but it was just the beginning. 10 years later, in 1915, Einstein published his general theory of relativity, and he added something that changed everything. He showed that space-time is not just a passive stage, it is a dynamic structure. It can bend, it can curve, and the thing that curves it is mass. When a massive object sits in space-time, it distorts the geometry around it. Space-time curves in response to the mass. The more massive the object, the stronger the curvature, and anything moving through that curved space-time, another planet, a beam of light, a falling apple, follows the curved geometry. It follows the straightest possible path available to it through the warped space. That path curves toward the massive object. To an outside observer, it looks like the object is being pulled, but nothing is pulling. The geometry itself is bent, and the object is simply following the bend. Here is the way I like to picture it. Take a flat rubber sheet and stretch it tight. That sheet represents flat space-time. Space-time with no mass in it, no curvature, perfectly uniform. Now place a heavy ball in the center of the sheet. The sheet sags, it curves downward around the ball. The geometry of the sheet has changed. Now roll a marble across the sheet. The marble doesn't go straight anymore. It curves toward the heavy ball, not because the ball is reaching out and pulling the marble, but because the sheet between them is no longer flat. The marble is following the curved surface. It's going as straight as it possibly can on a surface that isn't straight anymore. That is gravity. The heavy ball is a massive object. The rubber sheet is space-time. The curving of the sheet is the effect of mass on space-time geometry. And the marble's curved path is what we call gravitational attraction. No pull, no reach, no force transmitted across empty space. Just geometry, doing what geometry does when it's curved. Now I want to push past the rubber sheet, because it has limits as a picture. The rubber sheet is two-dimensional, and it only shows curvature in space. But the full picture involves the curvature of time as well. And the time part is actually the dominant effect for everyday gravity, for things moving slowly compared to light. Here is what curvature of time means. Near a massive object, time runs slightly slower than it does far away. This is not a metaphor, it is a measurable, confirmed physical fact. Clocks on the ground floor of a building tick very slightly slower than clocks on the top floor. Clocks on Earth's surface tick slower than clocks in orbit above Earth. The difference is tiny. In everyday life, we're talking about nanoseconds per day, but it's real. It's been measured directly with atomic clocks, and it has to be corrected for in GPS satellites, or they give wrong positions. This slowing of time near mass is what drives things to fall. An object near Earth is in a region where time runs slightly slower. An object farther from Earth is in a region where time runs slightly faster. The object moving naturally through space-time follows the direction of increasing time rate. It moves toward the region where its clock would tick fastest. That direction is away from Earth. Wait, that seems backwards. If objects fall toward Earth, why would they move toward increasing time rate? Here is the subtlety. Objects in freefall follow paths that maximize their own experienced time, paths called geodesics. On a curved spacetime where time runs slower near mass, the geodesic paths, the straightest possible paths, curve toward the mass. The object follows the curve of spacetime, and that curve takes it toward where time runs slowest, near the mass. The geometry of curved spacetime naturally funnels freely moving objects toward mass, not because time is fastest there, but because the curvature of the combined spacetime geometry points that way. I realize this is getting intricate, but it matters that you know it's real. It's not a hand-waving analogy. It's calculus applied to a four-dimensional curved manifold, giving predictions that match every measurement we've ever made. Let me show you what this picture explains, that Newton's picture cannot. Newton's gravity travels instantaneously. If the sun were to suddenly vanish right now, Newton's equations say that Earth would immediately fly off its orbit. The gravitational pull disappears at the same moment the sun disappears. No delay. Information traveling faster than light. Einstein's gravity cannot do this. In general relativity, gravitational effects travel at the speed of light. If the sun vanished, Earth would continue orbiting for about 8 minutes, the time it takes light to travel from the sun to Earth, before the gravitational change reached us. The curvature of spacetime propagates outward at light speed, just as ripples in a pond spread outward from a disturbance. This prediction has been confirmed, not by the sun vanishing, we can't arrange that, but by detecting gravitational waves. When two massive objects orbit each other and spiral inward, the curvature of spacetime changes as they move. Those changes radiate outward as waves, ripples in the fabric of spacetime itself. In 2015, the LIGO detector measured these waves for the first time, catching the signal from two black holes merging 1.3 billion light-years away. The signal arrived at the speed of light, exactly as general relativity predicted, not instantaneously, as Newton would have required. This single measurement confirmed not just that gravitational waves exist, but that gravity propagates at the speed of light. Newton's picture is simply wrong about this. Einstein's is right. Now let me bring this back to something you can feel right now. In your own body. You are sitting or standing somewhere. As you read this, you feel your weight. You feel the pressure of the ground or chair pushing up against you. You call this gravity pulling you down. But here is what is actually happening. In free fall, in a freely falling elevator, or in a spacecraft in orbit, you feel weightless, floating, no sense of up or down, no sense of weight at all. Einstein called this the happiest thought of his life. A person in free fall does not feel the effects of gravity. They are following the natural curve of space-time. They're geodesic, completely undisturbed. When you stand on the ground is preventing you from following your geodesic. Your natural curved path through space-time leads toward Earth's center. The ground is in the way. It pushes up against you, interrupting your free fall, forcing you off your natural path. That upward push, that constant interruption of the path you'd naturally follow, is what you feel as weight. Gravity isn't pulling you down. The ground is pushing you up. The pull you feel is the reaction to being held away from the path. Space-time is trying to send you on. This is genuinely, physically true, and it means that the most natural state, the state that requires no force, no push, no support, is free fall, floating, weightlessness. Standing on the ground is the unnatural state. Being held up by a surface is what creates the sensation we call gravity. Try to feel that right now. The pressure of the surface you're resting on. That's not gravity acting on you from below. That's a surface actively preventing you from doing what the curved geometry of space-time is asking you to do. I find that remarkable every time I think about it. The sensation we call gravity is actually the sensation of being held back. Now I want to talk about one of the most beautiful confirmations of this entire picture. The bending of light. Light has no mass. In Newton's universe, gravity acts on mass. So light should be completely unaffected by gravity. A beam of light passing near the sun should go straight. Newton's picture makes this prediction clearly, but Einstein's picture says something completely different. Gravity isn't about mass attracting mass. It's about space-time curvature affecting everything that moves through space-time, and light moves through space-time too. So light should follow the curved geometry near the sun. It should bend. Not only that, but Einstein calculated exactly how much it should bend. And his answer was twice what Newton would have predicted, even if you tried to make Newton's theory accommodate light. In 1919, during a total solar eclipse, British astronomer Arthur Eddington photographed stars near the edge of the sun. Normally, those stars are invisible. Their light is drowned out by the sun's brightness. But during a solar eclipse, the moon blocks the sun, and stars near its edge become briefly visible. By comparing the apparent positions of those stars during the eclipse to their positions when the sun wasn't nearby, Eddington could measure how much the sun's gravity had bent their light. The result matched Einstein's prediction, not Newton's. Einstein's. The light bent by exactly the amount curved space-time said it should. This was front-page news around the world. Einstein became an international celebrity overnight. Not because the physics was exciting to the general public, most people didn't understand it, but because the idea that the fabric of the universe was curved, that even light bent around massive objects, that space itself was not the flat, rigid stage Newton had assumed, felt like the ground shifting under everyone's feet, which in a sense it was. Today we use this effect routinely in astronomy. Massive objects, galaxy clusters for instance, bend the light from more distant objects behind them. This is called gravitational lensing. It distorts the images of background galaxies into arcs or rings. It lets us see objects that would otherwise be too faint or too far to detect. And it gives us a way to measure the mass of things we can't see directly, including dark matter, which bends light even though it emits none. Every gravitational lens in the sky is a confirmation of Einstein's picture. Every bent arc in a deep field image is space-time curvature made visible. There is one more thing I want to say, and it comes back to the word I started with. Pull. That word carries a picture with it. A hand reaching across, a force transmitted. Something active happening between two objects. And that picture, for all its intuitive appeal, is wrong. It led Newton to a description that was accurate but incomplete. It led 2 centuries of physicists to use equations without understanding what the equations described. It made gravity feel like a known thing when it was actually an open mystery wearing a mathematical mask. Einstein replaced the word pull with something far harder to picture but far more true. Geometry, curvature, the shape of space-time responding to the presence of mass, and everything moving through that shape following the curves it finds there. It took enormous courage to say that the most familiar force in human experience, the force every living thing has felt every moment of its existence, was not a force at all, that it was a property of the shape of the universe. It took even more courage to work out the mathematics, make precise predictions, and submit those predictions to experimental tests that could have proven the whole idea wrong. They didn't. The tests came back right. Every one of them. Mass doesn't pull. It curves. Gravity isn't a force reaching through space. It is space itself, shaped by the matter within it, guiding everything that moves through it, along paths that look, from the outside, exactly like attraction. But it isn't attraction. It never was. It's geometry. And geometry, when you really understand it, is one of the most beautiful things in the universe.